Yes. So as I mentioned before, conjunctions in space referring to occasions where two space objects. Nominally, I'll be talking about formation flights, but it could apply to other things such as contact with debris, other spacecraft that might be cooperative or not cooperative. But getting too close to something we like to avoid because you are unable to generally make quick interventions from the ground in scenarios like this. Ground passes can be very infrequent. Maybe you might get a few ground passes per day, you might get no ground passes per day. NASA tracks objects in orbit, or the Space Force tracks objects in orbit, and then NASA processes them and protects them, but they can only do that at a frequency of about once per object per day. So in order to have quick reacting, onboard autonomous execution of missions that we want to do, like we have the Visors mission, which involves two spacecraft coming within tens of meters of each other, which is a potentially precarious scenario, but we want to be able to manage that risk so that we can effectively guarantee that we are not going to have those spacecraft collide, which could cripple them, could create space junk. It's an ugly problem that we have to avoid at all costs, and we probably have to do it by letting the spacecraft take care of themselves and manage some risks, because again, we won't be able to intervene when these events might crop up, which could be due to something like a GPS outage. If we were to lose attitude control of the spacecraft, and we couldn't maintain our GPS pointing, and we lost our navigation, we may not be able to perform efficient controls on the spacecraft. There are scenarios where the human just won't be able to get there in time to react. So being able to predict these things and react on board is pretty critical. So there have been many ways that have been proposed to estimate the probability of things happening in space. We think generally in terms of lots of estimation. We're doing estimation of the states of spacecraft, their positions and velocities, orbit elements, relative orbit elements, and how can we use these distributions we get from state estimates, including the estimates and their covariances, to have a probabilistic metric on will these two spacecraft or two space objects collide. So there's been advances in different numerical integration schemes for doing the computation of like a probability integral over certain events occurring. There's been advances in sampling methods. We're doing sampling-based Monte Carlo methods in space. There's important sampling methods that can greatly reduce the number of samples you have to put into your Monte Carlo to get accurate modeling of these marginal results. Because we're talking about events that are unlikely to happen. Like a collision risk of 1% is unlikely to happen, but that's pretty high in terms of what we're willing to tolerate in terms of risk. So to accurately model these margins, there are efficient sampling techniques like Morton sampling, Monte Carlo shell sampling. There's optimization-based techniques for geometric separation metrics that I'll introduce later, and numerical integration methods, doing like different quadratures and integration paths for efficiently estimating probability intervals. You can consider this as one problem, as my spacecraft will need to respond to an anomaly scenario. You can consider another train of thought, which is I will never let my spacecraft get into an anomaly scenario. You can create your architecture with a planning that basically precludes these types of scenarios from occurring. So you have an EI vector separated relative orbit. This allows you to guarantee long-term passive safety between spacecraft. This doesn't work for everyone. There may be cases where you can't guarantee that you can maintain this while doing your mission goals. You may just want to have a reactive safety option. There are also many approaches that use like advances in swarm technology that's being used for some Earth. In deploying drones, use artificial potential functions and similar mechanisms to safely guide spacecraft or to ensure that spacecraft maintain safe states ongoing in an ongoing manner, so they don't get into these states if they function properly. But then these methods can also degrade due to failures of the spacecraft system, so it's a good idea to just be able to estimate these risks occurring. So I'll talk about two types of safety metrics. There will be probability of collision metrics / instantaneous probability of collision metrics. The probability of collision is simply the probability that your separation between spacecraft goes below some threshold that you're willing to tolerate in terms of the keep out zone. So D would correspond to a radius of the keep out zone or some other, it doesn't necessarily have to be a circle, it could be some other geometric constraint, but the probability that you violate this the probability that the spacecraft violate this constraint up to a tolerance they're willing to tolerate. Say, like, I want a 10 to the negative fifth chance that this occurs. And you can, we can evaluate that with different numerical methods of integrating the probabilities. There's also the geometric methods, which I mentioned before. So this will be a geometric separation between a physical point and a probability and a confidence interval on a random variable. So the distribution of the norm of the relative position vector, you want to ensure that it is always outside of a certain confidence level. So say like this shell, say we have a red keep out zone around our chief spacecraft, and then this shell represents a 3 sigma probability density function of the, or a 3 sigma covariance on the relative position of the B spacecraft and the chief spacecraft. We want to ensure that the 99% of all things that happen in this bubble do not happen in this bubble. So this is a more conservative estimate in a way, because rather than saying, I want to make sure that there's a less than 1% chance that they overlap, you're saying, I want to make sure that everything in here happens 99% of the time, everything outside happens 1% of the time. So you have a lot of space that's unused that technically you could be using and not violating your probability constraint. It is a little bit more conservative in that sense, but you do save a sort of counterintuitive risk that pops up if you focus just on probability metrics. And that is a probability dilution phenomenon where you can kind of get blindsided by a poor estimate giving you a low probability of an event occurring because the probability density is very low. So if you have like a very good estimate of your relative spacecraft position, you have a tight covariance on where the spacecraft is, you know where it is well, the probability density will be it'll be a denser function. So the integral over this volume where they share will have a higher value perhaps than this scenario where you have poor knowledge of the spacecraft. You might even be inside its 1 sigma, 2 sigma, 3 sigma confidence interval. But the integration of the probability density over the keep out zone is low because the density is lower in general. So there's no perfect trade-off exactly between knowing probabilistically that you're not going to collide and actually having that have value versus being a little over-conservative, but having a more strict guarantee that you're not going to be inside a zone of potential conflict. And then some authors have proposed different constraints you can impose on the covariance so that you can manage this risk and hopefully not fall prey to a poor estimate giving you a very low chance of collision. It crops up many times where people go in the conjunction assessment community think that probability is good, probability is bad, probability is good, probability is bad. But this is a problem I think most people are aware of. So I'll also introduce this frame. I know we have new students joining. Most people have probably seen lots of graphics like this, but I'll talk conveniently about motion in the RTM frame. So I'll be considering a binary spacecraft system with a chief and deputy. The frame will be centered on the chief, and its axes will be drawn to the radial position of the chief, the angular momentum of the orbit, and a clear vector including the right-hand triad. It's convenient to talk about motion in this frame because we can use concepts from passive safety, which I mentioned before, to kind of eliminate the need or screen off metrics that we can we know invariant we can't really rely on. Because the long track drift, for instance, is if you would see the T direction in the circular orbit is a very sensitive, unstable mode of motion where a small variation in your relative to major axes between spacecraft can lead to large drift and long drift between spacecraft. So focusing on estimation in the RM plane specifically to give us more robustness to these kinds of issues I talked about. I'll also talk about using this set of relative orbital elements. This is assuming those quasi-non-singular set of relative orbital elements. They are useful for describing the relative state of spacecraft, and we can use them to efficiently propagate the relative state of spacecraft over long time horizons while maintaining Gaussianity, which is nice for treating our random variables as Gaussians over a long time period. So by using this state, it allows us to do nice linear propagations of our covariances. And so now I'll discuss a little bit about doing some experiments and how I can generate different methods of doing the collision safety with or conjunction assessment safety metrics with different scenarios for modeling. So I can consider a Monte Carlo sampling of the state of spacecraft as a truth to get a baseline statistics for the system, knowing when separation between spacecraft are high or low, just by random sampling this. It is difficult to exactly know due to variations in things like the drag and differences between the models used on board and in the truth model to accurately generate distributions, so we can compare the Monte Carlo results as like a truth baseline for what happens with the onboard computations. And then these next two bullets will refer to what we can do onboard spacecraft. We can onboard spacecraft perform a propagation of the chief and deputy states, because we're assuming that we're performing navigation on the spacecraft and we know the state of your chief spacecraft and your deputy spacecraft. And you want to know in the future, are these spacecraft going to have a conjunction of it? I mentioned before PC and IPC. IPC is instantaneous probability of collision. That means at a specific instance in time, what is the probability that these objects are overlapping in the key path zone, versus PC refers to like an integral over the entire time of the IPC. And that would refer to like over an entire margin of time, over an entire region of time, what is your probability of collision. The IPC, I tend to think it provides like a lower bound for the PC could be. So if you're violating your IPC, you will certainly be violating your PC. So that I think is a handy surrogate to use instead of doing directly the PC, because that also involves, if you were doing the most rigorous statistics, it involves like a combinatorial set of combinations of states that are both inside and not inside the keep out zone over different time steps. It gets very messy, but the instantaneous PC provides a very good estimate that if any single point in time we are going to be violating our safety. So we can compute then both the IPC and the geometric separation indicator that I mentioned before. That's the distance to probability distribution. In a case where we perform integrated propagation of the spacecraft states, so a high fidelity onboard propagation, medium fidelity onboard propagation of the spacecraft dynamics, using models for geopotential and drag and other perturbation forces, and then perform updates on the covariance as well. Using the covariance in ROE space, we can perform updates linearly, which are very accurate over long time horizons, which is nice. Long time horizons, I'm also talking mostly about on the span of several orbits, not like days. And because we're talking about a case where we need the autonomous spacecraft response, where it needs to have a short-term encounter that might be a potentially dangerous scenario, not a long-term encounter. Or not like a 7 days out encounter. And we can compare that to if we were to treat our dynamics completely as a propagation of ROE, so the relative state representing the difference between the chief and the deputy state. We can propagate that linearly and compute the covariance updates in the ROE space there as well. And that is a very, very easy problem to solve on a computer. These basically go down in order of magnitude in the number of computations needed to perform each one. So I think on my computer, the double linear propagation is like milliseconds. This is like hundreds of milliseconds, like 50s of milliseconds, and this is like seconds. In terms of the accuracy, or in terms of the execution time, the accuracy is something that we need to examine. Are we gaining anything? Are we losing a lot of fidelity by using these lower fidelity propagation methods? And I'd also like to mention that these are not the only ways you can perform this. You can do a unscented transform to do updates on your covariance and pass them through the dynamics that potentially preserve more of the information. This is kind of just goes to like the lowest level of fidelity you can get by doing the linear updates. I will mainly be focusing on scenarios that are relevant to the bias suspicion. This presentation does not have many scenarios in it. This is ongoing, but this is for a visor-like formation where we have a low Earth orbit near circular orbit. 500 kilometers altitude is middle. It could be slightly higher, slightly lower. The lower you get, the more aggressive drag effects of it are, increasing density. So that's something we always want to be aware of, and you can use that to stress test your algorithms at like the highest possible density and see what the most maximal effects are. But the most important things I want to look at are the difference between, or the how the spacecraft range versus the size of the relative position covariances affects the accuracy of the different solution types, as well as how ballistic coefficient uncertainty will affect the accuracy, as that mainly that contributes fairly heavily to the long track effects. However, as I mentioned before, we can isolate long track effects by considering motion in the Rn plane, which tends to be fairly stable. So what I'm going to show you will be taken as a projection of the 3D RTN motion just in the Rn plane, which we can use as a more conservative surrogate for state separation that will be stable over a time period, or less subject to dynamic effects. In the truth, the Monte Carlo scenario, I model a 40 by 40 gravity model, the atmospheric drag, which comes from the Jeffrey Roberts density model, which I don't think many people use. I use it because it is plugged into the GMAT propagator I'm using behind some of my dynamics modeling. And then the onboard integration of the spacecraft absolute states is done using the same drag model with a lower fidelity gravity model. The state transition matrix propagated linear states for the ROE just models Kepler effects and J2 effects. There are drag inclusive STMs. However, in the experiments I've done so far, it did not actually crop up as an issue looking at just all-around motion. So this will be a visualization of what we're looking at. We start with a cheap spacecraft in the center with a small peak out zone of 5 meters. This is a feature of the visors CONOPS that we want to maintain a relative state estimate of the deputy in the RTN frame. And then again, this is a projection on the RN frame, on the RN plane only. And we can, from a measurement update from our filter, have a relative state covariance in the you could consider this coming from your representing a relative orbit element state a relative RTN state, a relative ECI state. For example, if I transformed this to a relative RTN state, relative position in the RTN frame state. And then we can perform a integration of the dynamics. So the mean of this represents the estimate of the deputy's position. We can integrate that. We can propagate this covariance of the positions of the potential theoretical positions of the spacecraft, and then we can propagate the samples of the sample distribution and see how this ends up and evaluate the separation metric, the geometric separation metric, and the probability of collision metrics. And just over a horizon of this is showing about one orbit how the covariance grows and shrinks, but the modeled the samples tend to be fairly well captured by the covariances over this time frame. This is again just one orbit. But 1 to 2 orbits tends to have fairly good match between the points and the analytically propagated distributions. So looking here on the left, we have the IPC calculation, and there's 3 lines here. The lines for the integrated dynamics and the STM propagated dynamics are nearly overlapping basically all the time. You'll notice that the Monte Carlo line has 0 probability detected. That's because this is showing in this scenario over 2 orbits what the probability of collision is for it sampled more coarsely over this time frame. With these covariance ellipses, there are no samples that fall inside the Q-dozen. So the Monte Carlo detects that the probability of collision, instantaneous probability of collision at each point is 0. Whereas the probability of collision generated by the evaluating the distribution is a quadrature integrated analytical function. It's numerically integrated, but it's a probability density function that is gives us a non-zero value, but it gives us a very small value. You will see that this line showing the 99% the distance to a 99% confidence interval ellipse in the RN plane. The agreement between the integrated dynamics and the STM dynamics is almost exact again, but there is a fairly, you can see a more conservative gap in basically every instant to the true Monte Carlo dynamics, where we underpredict the separation. So the blue line is the true separation distribution at that point. We are consistently underpredicting it. This covariance starts with a meter level in the R and N directions. If we start with a smaller covariance, which is more typical of the filter performance of the VISOR's mission, we see still a similar, so if we model it, the initial error to be on the centimeter level, the gap between the true probability distribution and the linearly propagated ones are still maintained in the separation. The instantaneous collision probability is unhelpful in this case, but this is a case where the minimum separation does not get super low, so it is not surprising that it does not provide much information. It is basically 0. It's like numerical noise. This is 10 to the 25th, so this is not a significant result here. But you'll notice in general that the probability of collision spikes where the separation indicator spikes downwards. It's like right after 4,000 seconds, right after 4,000 seconds, right at 10,000 seconds, right at 10,000 seconds, which is, I think, fairly intuitive. As your separations get smaller, your probability of collisions increase. Yes, and then this is an ongoing effort to also capture the drag effects, which will surely be very impactful in the tangential direction. The effect of drag in both varying the difference between the modeled and the true and estimated ballistic coefficient of each spacecraft, as well as varying the effects with a more significant relative ballistic coefficient between the spacecraft. I think will be interesting to see how the gap in the true and the model dynamics grows, as well as considering that we didn't model any drag effects in the ROE propagation, the linear propagation of the ROE state, but it matched almost exactly in the both probability metrics to the integrated dynamics. So using the integrated dynamics was basically 10 times speed up for no gain at all in these metrics, but that might change with a more significant relative ballistic coefficient. So these are methods you can use to perform convention assessment. I can go into more detail if you want on how these metrics are actually generated. I don't think I covered really how these integrals are evaluated and how the optimization problem works, but if you would like to talk about that, I'm happy to, and that's mostly it.